In the previous video, we took a look at what a microservice is and why structuring our servers as collections of microservices is helpful. In this video, we'll take a look at the practicalities and use Flask to construct a functioning microservice. Microservices can pretty easily be divided up into those that use web technologies such as HTTP to communicate with each other, and those that use a dedicated inter-process communication or remote procedure called mechanism to communicate. There are advantages to each depending on the specific needs of a project, and neither is inherently easier to work with. But I'm going to refer to microservices that use web technologies to communicate as high level, because they're inherently closer to the level at which users operate. Conversely, microservices that use specialized protocols I'll refer to as low level. In this video, we're looking at high-level microservices which usually use HTTP to communicate and provide representational state transfer-based programming interfaces. Using stateless protocols for communication makes these microservices easy to load balance and easy to swap in and out for maintenance. For this type of microservice, we could use any of Python's several production-quality web application, frameworks, or toolkits. But we're going to use Flask. Flask is laser-focused on making it easy to write handlers for HTTP requests and doesn't really do anything else. That makes it very well suited to writing a microservice that processes a few specific requests while using minimal resources. Flask isn't part of a Python standard library, but it's easily installed using pip. As always, you can add --user to the command to install into your personal Python package library, and you can install it into a virtual environment if you prefer. Flask is designed to interface with a front-end web server or proxy using the Web Server Gateway Interface, or WSGI, which is standard for Python web applications. However, we'll just be using its built-in development server for our simple little demonstration. So what shall we build? Let's build a microservice that maintains a database of information about people: first name, last name, age, and for interest's sake, whether or not they're members of a particular club. We'll use HTTP's post, get, put, and delete methods to allow the microservice's clients to create, access, update, and remove records from the database. And we'll provide the data in JSON format, but accept input using the normal HTTP form encoding. Those choices are all very normal. Only slightly less common would be to have incoming data be in JSON format as well, which we accommodate by calling Flask's request_get_JSON function when we needed the data. Okay, so what boilerplate code do we need to get a Flask microservice on its feet? Not much, as it turns out. These 2 lines are sufficient to get the Flask system in place. It doesn't actually do anything except return 404, not found errors in response to any request, but it'll respond. So how do we make Flask handle a request? There are actually 2 ways to do it. One which is incredibly simple, and one which is more flexible and better encapsulated. The simpler way is to use the app.route decorator to tell Flask that a particular function will handle request for a given path. That's all that's needed, apart from making the function actually do something useful. However, for our microservice, we want to use HTTP methods on the same path to produce different results. We could use app.route and a bunch of if-else-if blocks in the function to handle that. But there's a better way. Flask supports pluggable view classes and specifically has a method view class that has a different handler function for each HTTP method. The appropriate function processes each request based on which HTTP method was used. There's a slight complication to this because we don't actually always want to use the same path. Sometimes we want an object ID in the path, and sometimes we don't. There's only a small complication though, because we could register the same pluggable view on several different combinations of path and method, which is exactly what the endpoint.register function here in endpoint.py does. Each registration of the view consists of one call to app.add URL rule. The first one registers the get method with no object ID and fills in value to use for the ID parameter when calling the get function. The second one registers the post method with no ID and no default because our post function doesn't accept an ID parameter at all. The third registers the get, put, and delete methods when there is an ID. Between those registrations, that covers all the use cases common to a single programming interface endpoint in representational state transfer. Now that we've got our method dispatching ready, how about we put together our actual handlers for manipulating person objects? Here we see our person API class, which has one function for each of the operations we want to enable on our person database. For the post and put functions, we get data from the request using the request.form object, which is a dictionary-like object containing the decoded data from the request body. As a side note, this looks like it's not thread safe, but it actually is. Everything in Flask is multi-thread and multi-process safe. It's just wrapped in a simplifying semantic layer that simulates a single-threaded single-process system. The post function doesn't have any code to handle missing data except for the member value. That's because if we try to access a missing value from request.form, an exception is raised that causes Flask to return a 400 bad request error, which is exactly the right thing to do in that case. The put function, on the other hand, handles those exceptions itself so that it can decide which values to update and which to leave alone. The get function might be called with an integer ID or with none for the ID, and needs to handle both cases. That's easily done with an if statement. In the case where the ID is a number, it's supposed to return the state of the object with that ID. If ID is none, it's supposed to return a list of all of the objects. All the methods return JSON formatted data, which is done by using Python's standard JSON package, and specifically the JSON.dumps function, which transforms Python data structures into JSON formatted strings. We also need to provide the content type header with a value of application JSON as a matter of good practice. Between those two things, in the return statement, we're also providing the HTTP status. That could be omitted, but since we're returning error codes in some places, it makes sense to include the status code, even when it's not an error. To do a test run of our microservice, we're going to need to start up Flask and tell it to serve our microservice. The demo Flask package also contains a module called test.py that we can use as a client that connects to our microservice and put it through its paces. It will add, delete, list, and modify a couple of database entries, and also try out a bad post request to show that the error handling is working. There's one more part of the Flask demo microservice that we haven't talked about, and won't in detail. That is the person.py file, which contains a simple interface with a SQLite 3 database for actually storing and retrieving objects. Feel free to look at it, of course, but it's not particularly relevant to the topics of this section. And a production system should probably use SQL Alchemy, Redis, CoachDB, etc. In this video, we looked at the details needed to use Flask to create a RESTful microservice and put that knowledge to use by building a simple person management microservice. In the next video, we're going to look at using the nameco package to create microservices that communicate using remote procedure calls instead of HTTP methods.